Given an n by n matrix grid, each entry is the elevation at that cell. Rule: at time t the water depth is t, start at the top left, each move is to a 4 neighbor, and both cells on the step must have elevation at most t, return, the minimum t so you can reach the bottom right corner. Constraints: n between 1 and 50, entries are distinct integers from 0 up to n squared minus 1. Example: grid is row 0, 0 then 2, row 1, 1 then 3. At t equals 2, the cell with elevation 3 in the corner is still too high, so you cannot finish there. At t equals 3, every cell is allowed, and one path is 0 to 1 to 3 along the bottom, or 0 to 2 to 3 along the right. The largest elevation along such a path is 3, so the answer is 3. Second example, 5 by 5 spiral elevations. The highlighted cells show one optimal walk, along the top row to the right edge, down the right side, then through the middle and along the bottom row into the bottom right corner. The highest elevation we step on along that route is 16 at row 2 column 4, so the minimum time is 16. From the 0 cell you try to step onto the neighbor at height 10. While t is still 0, that step is blocked because the right cell is too high. We raise t to 10, now both ends are allowed and the step opens. Among paths from start to goal, the time you need for one fixed path is the highest elevation along that path. One story climbs to 50, so you must wait until 50. Another never exceeds 20, so 20 is enough. We want the path whose worst cell is as low as possible. Depth-first greedy moves can mislead. At a fork, the gentle 5 looks tempting, but that lane ends at 200. The branch that begins at 100 stays flatter overall, capping the pain at 100. So a purely local rule does not guarantee the global minimum, you need a search that compares bottlenecks across options. Dijkstra on this graph keeps, for every cell, the best bottleneck discovered so far. A min heap always expands the currently cheapest frontier state. That behaves like water flooding the lowest unlocked neighbor first, so when you first reach the goal, the worst height encountered along the way is already minimized. Solution on this 4x4 grid, each cell shows elevation. We run Dijkstra where the cost to reach a cell is the worst elevation encountered along the way, the crossing time for that route. The start has height 0, so we push tuple cost 0 at row 0 column 0. A min heap always extracts the smallest cost next, so we always expand the easiest frontier first. First extraction removes the start. Its neighbors are row 0 column 1 at height 3, and row 1 column 0 at 11, so we push candidate costs 3 and 11. The heap orders them so 3 is on top. Mark the start visited in blue, and record the cost just popped, 0. Next we pop cost 3 at the top neighbor. Even though 11 was already in the queue, 3 is smaller, so we explore the gentler cliff first. That is why a min heap is the right waiting line, it always serves the cheapest bottleneck next. We pop cost 4 at the next top row cell. The heap now mixes moderate and large keys, 11, 15, 12, but the root is still the smallest bottleneck, not the tallest elevation sitting inside. So discovery order does not matter, the array structure keeps the next best extract on top. Pop cost 5 at the middle corridor cell. Each relax can introduce new candidates, the heap lets the smallest bottleneck jump ahead of bigger stale entries. That mirrors the story from the intuition scene, global order comes from comparing worst steps, not local slopes alone. Next comes cost 6 at the center cell, then another 6 reaches the bottom row. Notice the bottom row tile has elevation 1, yet its stored cost stays 6, crossing time never decreases once you paid a bottleneck. When we finally pop the bottom right corner at cost 6, we stop, that is the minimum swim time. Here is one optimal route along the top row, through the 5 and 6 in the middle, then down to 1 and 2 on the bottom edge into the corner. The highest elevation on that walk is 6, matching the first goal pop. So the algorithm's bottleneck cost is exactly the minimum time to swim. N is the side length of the square grid, so we have n squared cells to search. Time is O of n squared log n. Dijkstra visits each state at most once, and the binary heap makes each push or pop logarithmic in the number of states, which is n squared. Space is O of n squared for the distance table, and the heap can grow on the same order in the worst case. Pseudocode for swim in rising water. We keep the best bottleneck distance to each cell in dist, and a min heap of tuples d, row, col ordered by d. We pop the smallest d, skip stale entries, return when we reach the bottom right, otherwise relax each neighbor with nd equals max of d and the neighbor height, and push improvements. N is the number of rows, the grid is square. Dist stores the best crossing time found so far to each cell, start at infinity. Top left cost is its own elevation. Heap entries are bottleneck d with coordinates, seed the start cell. Main loop until the frontier is empty. Pop the smallest bottleneck state. Ignore outdated heap entries whose d no longer matches dist. If this cell is the destination, return d as the minimum time. Try each for neighbor. New bottleneck if we walk onto that cell is the max of the old bottleneck and its height. If we found a strictly better route to the neighbor, update dist. Write the improved distance into the table. Push the neighbor state onto the heap. After the loop, return the best bottleneck distance at the bottom right cell.